All right, this video is going to address what we call direct variation, but it's going to start off with a little bit of an introduction, basically reviewing slope-intercept form. So again, you notice the two equations we have up top here, y equals 3x and y equals negative 3 halves x. Basically, both of those are in y equals mx plus b form, but notice when we've got 3x, that means our slope would have been 3 because again, whatever is multiplied by x is 3. But notice we have nothing added on. So added on to that 3x basically is a hidden 0, right? We never have to write plus 0. So our y-intercept right now, or what we often call the b value, would be 0, which just means that again, that's the coordinate saying, well, if it's a y-intercept when x is 0, right? We haven't gone left to right at all. We would get a y value of 0. Right? If I plugged in x was 0, 3 times 0 would be 0. We could do this the old-fashioned way and basically make a big table. And you'll notice again, when x is 0, y would equal 0. So again, we're going to start at the origin. Now we could just plot those other points, but notice we know that slope. So the slope of 3 tells me, well, I'm going to rise of 3, right? Because that's the same thing as rise of 3, run of 1. So I'm going to rise up 3 and then go right 1 and plot another point there. And I can continue to do that, plotting another point a little bit off my graph, but it would work. Or if I put a couple of negatives on there, remember negative 3 over negative 1 would also be go down 3, left 1, down 3, left 1. And again, I could connect those points with a nice straight line because technically all the points in between those points are also on my line. And again, by counting by ones, both on the x-axis and y-axis, we can draw ourselves a nice line right through the origin there. Now you'll notice our second equation, it's the same idea because that's plus 0. All I really need to identify is that m would be negative 3 halves with a b value, again, a y-intercept through the origin. Or again, if you plugged 0 in for x, anything times 0 is going to give you 0 back for an answer. So you'll notice again, we're going to go through the origin on this one. Again, the slope being negative 3 halves means go down 3, right 2. Down 3, right 2 this time. Or I could go, if I plan that negative to be on the bottom, what if I went positive 3, left 2, right? Positive 3 vertically, left 2 horizontally, making that negative basically be the horizontal component. Well, now we get that nice, as straight as I can draw it line there. Again, assuming I was counting by ones, I'm going to go ahead and label that first tick mark this time on both of those. But again, we get a nice smooth graph starting at the y-intercept and again graphing out our slope. Negative 3 vertically with a positive 2 horizontal, or positive 3 vertically with a negative 2 horizontal. We've got to work that negative either top or bottom, just not both. And notice if we did plot our points, notice those points, negative 1, 1.5 would have been right on my line, right? Positive 1, negative 1.5 would have been right on my line. If I would have plotted those, maybe my line would have been just a little bit straighter. It looks like maybe I went a little low with the red line, but you get the idea. Now, both of these equations, because they had y-intercepts of 0, would be considered what we call direct variation. A direct variation equation is basically a simplified y equals mx plus b equation. It's just y equals, and what we have here is ax, and we could have easily called that mx, but again, y equals ax, and notice nothing added on. Nothing added on. Now, some people like to write their direct variation equations a little bit differently. If I divided by divided by x on both sides, you would notice we would get y over x equal to, again, divide out the x, we would have just a on the other side. So it could also be written as a equals y over x, right? Or the comparison of y to x, which sometimes helps you remember it. Again, that's a lot like the slope formula, right? Y's over x's. So that might not be a bad way to remember it either. I like this equation. I think it's fairly simple, fairly basic. Y equals ax. A is what we call the constant of variation. As x goes up by 1, right, a tells you what y is going to do. So similar to our equations back here, as x increased by 1, you'll notice that y went up by 3, right? Negative 3, 0, 3, 6. As x went up by 1 in our second equation, right? Negative 1, 0, 1, 2. We went up by, down by, right? Negative 3 halves. 1.5 down to 0, down to negative 1.5, down to 3. we went down by 1.5, right? For every x value we went up. So direct variation just tells you, well, hey, as x goes up, y goes up, or as x goes down, y goes down, and how that's going to work. Again, the constant of variation tells you exactly where that's going to go as x increases. So again, looking at our equations down here, y equals negative 1/2 x. Well, the a value, the constant of variation, would be that negative 1/2. Or in that second equation, you'll notice y equals 4x. It's got to fit perfectly in this formula. Y equals just a number times x, nothing added on. Basically, a would be 4. Graphically, a couple things we want to remember. The constant of variation is basically just what the slope was. Again, as x goes up by 1, it's how y is going to increase, right? Rise over run. Y does what as x goes up 1? And notice the blue line, y went up 4 as x went by 1. On the red line, y went down 1/2 as x went over right 1. Down 1/2, right 1. Down 1/2, right 1. Or down 1, right 2. Again, gets you, kind of skips a point, but you get the idea how that slope would work as the constant of variation. The second thing is, and you'll notice these two equations, just like the two we had on the last screen, the graphs of all direct variation equations pass through the origin. Your y-intercept will always be 0, 0. A couple of things we want to be able to do with direct variation. Well, if they give you some equations, we want to determine is something direct variation or not. And if it is, it must have a constant of variation, so can we identify that? Well, in order to do that, remember our basic equation is that y equals ax. So I need to be solved for y. So I'm going to go in that first equation we have over here at the left. I'm going to subtract 2x because I want to get this y totally by itself on the left side, right? 2x minus 2x is going to disappear, and 0 minus 2x is just negative 2x. Well, that looks like it fits our formula, and I would say that a equals negative 2. So tell whether or not it does. I would say yes. And again, what's your constant of variation? I would say a equals negative 2. Let's do the same thing on the equation in the middle. Again, if I want to solve for y, I'm going to add x here. And I'm going to add x over to the right side, which basically on the left leaves you with y, right? Negative x plus x disappears. Y equals 1 plus x. Now that's not just the number multiplied by x like it's supposed to be, right, for direct variation. That's a number added on. So this one I would very simply say no, that's not direct variation. I can't name the constant. I'm not just going to name the slope. Like we said, the constant variation and the slope are similar. If it doesn't fit direct variation, if there's anything added on, then we're just going to say no, it wasn't. All we care about is direct variation here. And the last equation, it looks kind of messy, but again, let's start off the same way we did last time. Negative 4x, subtracting on both sides. So we're going to have a negative 5y equals negative 4x. Then I'm going to go ahead and divide by negative 5. Again, to get that y totally by itself, right? Negative 5 divided by negative 5 should cancel away nicely, right? And negative over negative makes a positive. 4 over 5 is 4/5. And again, if it's 4x over 5, I can just take that x off the top of the fraction, right? Just like saying 4 times x divided by 5 is the same thing as 4 divided by 5 times x. And I get a nice equation there, which again looks like a number multiplied by x. So I would say yes, a equals 4/5, or my constant of variation would have been 4/5. Now, what do most direct variation equations look like, or how do they apply to the real world? Usually they're going to start you off a lot of times with this kind of information. Write a direct variation equation. So the first thing I'm thinking is y equals ax. However, relating x and y when x equals 5 and y equals 20, which means I don't want just this basic equation. I want to know relating x and y, so I can have x and y in my equation. I need to know what a is. Notice they didn't say relating x, y, and a. I need to know what a is. I need to know the constant of variation. So let's take the information we know. We'll start off doing that. Let's find the constant. When y is 20, right, a times x, a times 5, should give us 20, right? If I fill in the x and the y, which means divide by 5, and 4 equals a. Step 1 to a direct variation equation is find the constant. Step 2, write the equation. So I'm going to take out a then, And again, knowing this information relating x and y, for every point in my problem right now, y equals 4x should get me the correct points. And then the third thing I typically need to do is, okay, what do they want me to do with that? Now, do they want me to go graph that? Do they want me to make a table? And it looks like down here at the bottom, then find a value for y. So I'm going to find y, knowing that a is 4 when x is 10. So I'm going to write that out, basically saying 4 times 10, which is 40, and I'm going to find that third part. So oftentimes it's find the constant, write the equation. Don't forget, that's what they wanted us to do, was write a direct variation equation knowing the constant. And then finally go do what they want us to do, find that y value. Real world problems or application problems sound very similar to that. The income at a store varies directly, which immediately makes me think direct variation equation, as the advertising budget. When the owner spends $3,000 a month, their monthly income was $120,000. That's the given. That's the given. So that's like on our last problem where they gave us x is 5 when y is 20, right? Well, this time we spent $3,000 a month, right? When our gross monthly income was $120,000. So again, the income at the store varies directly. So I'm going to call that income varies directly, A times something times the advertising budget, right? The ad budget. So let's call that budget. We'll call it B. Well, the store owner spent $3,000 a month. Well, that sounds like the advertising budget. So the budget was $3,000 when the income was $120,000. Divide by 3,000, right? Because we were multiplying by 3,000, I'm going to divide that away, and A will end up equal to, well, very simply, I would take off the 3 zeros off the top, 3 zeros off the bottom, and 120 divided by 3 is a simple 40 here. Which means my equation then just became my income equals 40 times the budget. If the owner increases their ad budget to $5,000 a month, well, how much income should we expect? Well, the income should be equal to 40 times the budget, 40 times 5,000. Oops, one too many zeros there. And the income should be equal to, well, 4 times 5 is 20. We've got 4 different zeros going on, so another 1, 2, 3, 4. I would say that we should expect an income of $200,000, right? Gross monthly income. I hope that helps you with direct variation. If you have any questions, make sure you talk to your teacher. Otherwise, have a great day.